Okay, can you still see my screen?
Yeah, ma'am.
Okay.
It is good.
So the first question is unrestricted grammar for the following language: a to the n square, where n is greater than equal to 0. So we've seen how to construct how to construct a unrestricted grammar for a to the 2 to the n. So now we want a to the n square. So first question is, when I say n square, so for example, for a to the 2 to the n, we had a strategy, right? We constructed, we had constructed n a's, and the idea was that every time every time I skip over, every time I go past this, I'm going to be creating I'm going to be creating 2 to the I minus 1 if I skip past I such is. Or rather, what I do is I keep doubling. So every time, if from this A I moved left, look at the number of A's I created. The next day when I move left, I'm going to create double the number of A's. Right? This was the idea. Now for n square, what can you do? Can you think of any relation for n square? Because 2 to the n, you can think of this as 2 whole square, then this whole square, and so on. Right. So that's why I could double. So any thoughts on how to do this? Yeah, okay, can you give me an algorithm first? If I had to recognize this language a to the n square, can you give me an algorithm? Anything, non-deterministic algorithm is also fine. You can hear me, right?
Yes, sir.
Okay. Can somebody give me an algorithm for this, a Turing machine algorithm, to prove that this language is recursively enumerable? what will be an algorithm? So here is my algorithm. You guess n and then you check whether the input is of the form a to the n square. Can you do this in a Turing machine? Are you guys still here? Okay, somebody answer.
Yes, ma'am.
Yeah, okay. Yeah, so you have to tell me why. Why can this be done in a Turing machine? Saransh, are you there?
Yes, ma'am. I'm just thinking about it.
Okay. So how will you guess n? What do you do when you're guessing something? Okay, so what is n square? N square is basically n plus n plus n and so on n times, right? So now can you tell me how did you do step 1 and step 2? Somebody else can also try. Whoever has the answer can tell me. Okay, so Aditya Pandiri, are you there?
Yes, ma'am.
Okay, can you tell me how this will be done?
I'm thinking. Yes.
Okay, so this simple algorithm, let me give it to you. What is the meaning of guessing n? So this is same as, you can say that this is copy a to the n uh, up to a certain point. Okay, so you, okay, let me say copy a. Copy a is up to a certain point, and this is the guess for n. Okay, so in a separate track, you are copying a's up to a certain point. Now you have to check. So suppose you have, this is your input track, and you have certain a's written over here. In your in the second track, you have copied up to a certain number. You decided to copy up to some place. Now you have to check whether there are n such versions of this substring, right? Then you will be able to check whether this is n square or not. At some point you will have a blank, right? So you basically have to check whether there are n, so if the length of this is I, you have to check whether there are I copies of this. And how do you do it? So you go from left to right, move from left to right, and every time maybe you mark this and you mark this, then mark this, keep doing this. At the end, you erase these marks. You come back in the second tape, you erase these marks. In the second tape, you again go back to the same tape, but you have a different mark, maybe like something like this, which says that out of the IAs that I have copied, for one such A, I have marked one copy of, so if I have copied IAs, I want I copies of this string, right? So this marking indicates that I have marked one such copy. The second time you will mark this, meaning I have two such copies. When you have marked it all, then you have I such copies. And now if in the input string you still have some A left to be read, then it is not of the form A to the 2 to the n for this particular guess of n. Sorry, it is not of the form A to the n square for this particular guess of n. Yeah, but since you are in non-deterministic Turing machine, there will be a path where you are guessing correctly. Is the algorithm clear? Any questions regarding the algorithm? Okay, so let's try another algorithm. Algo 2. where I'm saying that n square, this is something we learn in school, n square is 2i minus 1, I going from 1 to n. Do you guys know this?
Yes, ma'am.
Right? So then n square is basically 1 plus 3 plus 5 plus
7 odd.
yeah plus 2n minus 1, right? Okay, so now can you give me, so basically no matter what your n is, this is the format you're going to get. So now can you think of a deterministic algorithm that does this? So instead of generating 2i, I am generating up to 2i minus 1 and then just one more, right? So give me a non-deterministic Turing machine. So now non-deterministic Turing machine is also formed. So how will you generate a to the n square from this formula? You generate it like this. So suppose I did something like this. I'm just generating. Later on I can check. So suppose first I generated A, then I put a hash. Then for the next thing, I copy whatever I have copied between two hashes. So let me start with a hash. Then I wrote A, then I put a hash. Between two hashes, whatever I have, I copy it, and then I add uh, two more A's. Okay, now I put a hash again. Whatever I have, I copy it and I add two more A's. So these adding two more A's you can remember in your state space. Again, I put a hash. Whatever was between the last two hashes, I copy again. A, and I add two more A's. So notice that I have generated one, then three A's, then five A's, then seven A's, and so on. Right? So now what I can also do parallelly is, let me just erase this part. What I can also do parallelly is, as I'm generating these A's, look at my input tape. So I have this, and then I have some A's. So every time I'm generating an A, you mark an A over here. So here you generated 3, you mark 3. Then you generate 5, then you keep marking. Okay? At some point, if you reach a blank space and you are still in the, so suppose you have ended with a hash and you encountered a blank space, then what can I conclude?
We, it's not in the form of reference.
Not in the form. Why?
Input is not in the form of reference.
Why? See, if I put a hash, everything before the hash, look at the number of A's. It is in the form a to the for some I. It is of the form a to the I square, right? Yes or no?
If we don't reach a blank space, if we don't reach a hash,
No, yeah, right. Are you saying that if I don't reach a hash or a blank space, then I'm not in the form a power
Yes.
n square?
Yes.
Yeah, so my question was, suppose you have reached a hash and you have reached a blank space in the input tape, then you can conclude that the input tape started off with an a power n square for some n.
Yes.
For anything else, you can say no,
Yes.
right? So basically, I am generating one step at a time. I'm generating 2i minus 1, going through all i's. Okay. So now can you think of an unrestricted grammar? Okay, I think for the interest of time, I'm going to give you a grammar. Can you see it? Can you see my writing? Okay, so I'm going to give you a grammar and you guys please verify whether this is fine or not. Okay, so this is the grammar that I have come up with. You can come up with your own, but I mean, please argue for yourself. The idea that I'm trying to capture is the following: that you first, so I know that n square is equal to summation 2i minus 1, I going from 1 to n. So basically what I will do is, I have this left marker and the right marker is, let's say, hash. I also have, let's say, T indicates the pointer, the tape head. A dash will be something that generates one single small a. And capital A's will be something that generates at least two small a's. Okay, so now, so suppose so using this G, I will be generating some n minus 1 number of capital A's and one A dash. So now T is going to move from left to right using these, and till it hits this hash, the right hand marker. Now every time it encounters an A dash, it is generating one A. And every time it is encountering an A, it is generating two A's. Every time. Now once T moves and hits this right hand marker hash, then I'm going to be using this to say that um, I will try to forget the last capital A or the last A dash, whichever I encounter. I will try to forget that, meaning that if I started with n minus 1 A's and 1 A dash, now after T has moved completely to the right, I will have n minus 2 A's and 1 A dash. Then finally, at one point, I will have just one A dash, and then finally, I should have nothing left. Okay, so this is what these two things are doing. Also, with small a's, I should be able to, once I have generated a small a, I will try to move my right hand marker so this is not exactly the right hand marker, but I will try to move. This is sort of, it's a right hand marker up to the last non-terminal that appears in my sentential form. And now once I have done this, look at this R. This R is basically the tape head right before the this hash symbol. Now I will try to get this R back over here in front, just after L. Once R is just after L, I will generate another T in place of R, and I will continue doing this. So every time T goes from left to right, I will have generated for every A dash 1A and for every A 2 A's, 2 small A's. And I will have forgotten at least one such non-terminal, the last non-terminal amongst A dash and A's. And finally, if I have forgotten everything and I just have LR hash remaining, notice that there can be some A's after hash. Then I will just forget about all the remaining, these can be the LR hash can be the only non-terminals left. Everything else is A's. So then I will forget this, I will put this as epsilon, and I will only have a string, a sentence with A's. Now notice that the way I have used my A dashes and capital A dash and capital A's, I will have generated summation of 2i minus 1 A's, which means that I will have generated A to the n square as my sentence. Okay, but please verify this. Is the idea clear? Anybody has questions? Can you hear me? Am I audible? Hello, am I audible?
Yes, ma'am. Yeah.
Okay, so then, okay, so let's try, we'll come back to unrestricted grammars. Let's try something from reductions. So this is something that you can try and do using the definition of reduction. So suppose A is a language over sigma and B is a language over chi. And suppose A is less than equal to, sorry, A is many one reducible to B under some reduction map. But we also know that this reduction map is onto. Okay, so it is surjective. So then can you prove that I can also construct a reduction map such that which certifies that B is many one reducible to A. So just for your reference, suppose this is sigma star and this is chi star. Suppose this was A and everything else is A bar. Then I know that this reduction map, let's call this sigma. Then this was mapping it to B. And A bar was getting mapped to B bar. But the point is it is also surjective. So for all W in chi star, there exists a pre-image in sigma inverse W, right? This is what it means to be onto. So basically what we are asking is, so now if you have to prove B less than equal to A, one way of doing it is identify a pre-image and map each W to that pre-image, right? Because I'm satisfying yes if and yes in A if and only if yes in B, and no in A if and only if no in B. If I just could calculate one pre-image for sigma inverse W, then I would be able to get let's say some pi which maps from chi star to sigma star, and the idea of pi is select I mean every W will be mapped to a pre-image of W, some pre-image that we have identified. So now the point is, how do I identify pre-images under sigma? So this has to be a total Turing machine, right? That identifies this pre-image, because this pi has to be computed by a total Turing machine, just as this sigma was computed by a total Turing machine. It could be a non-deterministic total Turing machine also, but it has to give a yes or a no in each of the, if it's a non-deterministic Turing machine, it has to give an explicit yes or no in each of its parts. So how will you design a total Turing machine? Could be non-deterministic such that it computes pi. So basically such that for any W from chi star, it is going to compute one pre-image under sigma. So I don't care about the running time. All I want to know is whether I can compute in finite time. So anybody? So suppose I have a non-deterministic Turing machine. What can I do about this pre-image? I don't know which amongst sigma star is a pre-image for a particular W. So for this non-deterministic Turing machine, input is W from chi star. How do I determine a pre-image? What can I do to get this pre-image? Okay, so basically, if I am designing a total NTM, then I can guess a pre-image of W. And then check if sigma W, sorry, pre-image V of W, and check if sigma V is equal to W. Okay, so sigma V can be computed like total Turing machine for sigma used as a subroutine. Okay, and so suppose, so if yes, then output V as pi of W, and if no, so guess is wrong. So there will exist, since this is an onto mapping, there will exist a correct guess. In which case I will be able to output that guess as pi of W using this algorithm. Any questions? Okay, then let's try one more problem. Okay, so you are given the problem of whether a Turing machine M on a given input X re-enters its start state. And the question is whether this is undecidable. So let this problem be called pi. So pi takes as input M and X in some form, in some encoding. You can assume that you can take this in some encoding X, and let's say S is the start state. So decide if M re-enters S on X. So decide meaning you have to check if there exists a total Turing machine solving pi. Solving meaning there is a decider for pi. And you have to prove that this is undecidable. So what can you do? So let's try a reduction. What will you reduce from? Can you give an example of an undecidable problem? Okay, Abhijit Singh, are you there? Abhijit Singh? Bhagoti, are you there? Vismay Parija? Buddha Mohan Chandu? Khushbu Singhania?
Yes, ma'am.
Okay, so can you give me an example of an undecidable language? If others know the answer, you can also go ahead. What is give an example of an undecidable language? Okay, anybody has an answer?
Halting mission. Halting.
Sorry, halting problem.
Yes.
I couldn't hear you. Did you say halting problem?
Yes, ma'am.
Okay, so let's start with the halting problem. We will reduce from halting problem to this problem pi. Okay, so what will the reduction do? Basically, if halting problem, uh, for some instance of the halting problem, we will be constructing some n hash y, let's say, such that m halts on x if and only if n re-enters start state on y. Right? So now, can you think of an easy? Can you think of an easy we can like easy additions to m such that you can construct n and y from m and x such that if m halts on x, you can ensure that n re-enters the start state, otherwise not. Okay, so one basic thing to do is n has a new start state. S dash, and like we will try to restrict when S dash is entered. Okay, so maybe for the tape of n, we put in a special symbol as the left hand marker, and the left hand marker for m along with the input of m input. Okay, no, let me do this on a separate track. So I will have a special symbol for n, and then I will put in maybe like maybe the input for n, the traditional input for n, I will put it in after this. I will have a special symbol for this is my left hand marker for n. Then there will be for any input, I will put the traditional left hand marker first, and then so basically I will shift the input. Let's say y is the input. I will shift the input y to the left, sorry, to the right, one place to the right, and put in the traditional left end marker. And I will add a transition S dash and this special left hand marker. Transition to this is S left hand mark S special left hand marker and right. Okay, after this, it is going to be the transition function of m. And in the construction, I will make y equal to x. So now notice that if m and y equal to x, and on a separate tape, I will simulate m on x. Or you on this y itself, you can simulate m. On a separate tape, you store information of store info of simulation of m on x. Okay, so now if m halts on x, then after this step, we re-enter S dash. And if m doesn't halt, then only delta m transitions are used. And therefore, and we will enter a loop inside delta m using delta m itself. So therefore, S dash never re-entered. Okay, so we constructed this m hash x to n hash y. We constructed n in such a way that its starting state is separate from all other states of m, and in one step we go from starting state, this special start state of n, to the original start state of m, and then we also set y to be x, and then we basically n basically simulates m on x. If m halts, then n has one more transition, which transitions into the into the start state of n, which is s dash. And if m does not halt, then we stay within the transitions. Our next configurations are determined by the transition function of m itself. So therefore, we never re-enter this start state s dash, which is not a state of m. Construction clear? Any questions? Okay, so let's try one more problem. So AL 2022 is the set of all machines. You can think of this as a language because every machine can be encoded as a binary string. So all machines, all Turing machines that accept at least 2022 input strings. Okay, so part one is prove that AL 2022 is recursively enumerable. So you have to give me a Turing machine algorithm for AL22. So input of AL22 is some n, some encoding of n. Now what can you do? I can even give a non-deterministic Turing machine because non-deterministic Turing machine is equivalent to a deterministic Turing machine. Okay, in a non-deterministic Turing machine, if I want to see whether there are at least 2022 input strings that are accepted, what should I do? I have the power of guessing, right? What should I do? Okay, so what I can do is, I guess 2022 strings uh, which should be accepted by M, and then I run M on each of them. So I can use round robin or not, because if M enters a loop, then I know that this guess is not correct. There will be one guess where M has finite computation history for each of the 2022 strings I have guessed. Okay, so there exists one. So if yes, then there exists one guess of 2022 strings such that M has finite computation history for each of the 2022 strings and accepts each of them. So if no, then it is possible that it is possible that for the if M is not such a Turing machine, then it is possible that some of the guesses will lead to explicit no's. Suppose all of them in finite computation history, M decides that each of these 2022 strings or some of these 2022 strings are not accepted by you. So these will be explicit rejection of these guesses, and there could also be implicit rejection, meaning that on some of these strings, that the strings that you have guessed, you enter a loop, which means M is going to implicitly reject those strings. Okay, so we designed a non-deterministic Turing machine to check whether a non-deterministic Turing machine for AL 2022. Okay, so now quickly you have to prove that AL 2022 is not recursive. So part B is AL 2022 not recursive. So as before, I'm going to give a reduction. I'm going to try for a reduction. HP reducing to AL 2022. So have you seen any of the examples before that, I mean, if so you take M hash X and you have to construct some N, and M falls on X if and only if N accepts at least 2022 strings. So have you seen any examples where if M halts on X, then N has a large, the language of N has a lot of strings, and if M does not halt on X, then the language of N maybe does not accept any string. Have you seen any examples like this in the previous classes? Okay, so then let me just give you a hint and then we can stop. So you try to construct N such that language of N is equal to sigma star when M falls on X, and it's equal to the empty set when M doesn't halt on X. Okay, so you construct N, your reduction should construct such an N which has such that that N satisfies this. And notice that if it satisfies this, then M halts on X implies that N accepts at least 2022 strings, and if M doesn't halt on X, then it doesn't accept any strings, so in particular it doesn't accept at least 2022. Okay, so the other hint is that you have seen such a construction already in the lectures. So please try this on your own. I think we left out 2 questions. So anyway, you can try them on your own. So we left out a question on shuffle and another question on unrestricted grammar. You can try it on your own. Okay, thank you.